Hello dear students, hope all of you are well. Today we are going to discuss NCERT solution of class 11 chapter number 5 states of matter. You can see the first question, what will be the minimum pressure required to compress 500 decimeter cube of air at 1 bar to 200 decimeter cube at 30 degrees Celsius. So what the things are given, first of all we have to write that things. P1 is equal to 1 bar, V1 is equal to 500 decimeter cube, V2 is equal to 200 decimeter cube. Since the temperature remains constant, the final pressure P2 we have to calculate, right? So according to the Boyle's law, P1 V1 is equal to P2 V2. So P2 will be P1 V1 upon V2. We have to just put the value 1 into 500 upon 200 bar. That is equal to 2.5 bar pressure. Therefore, the minimum pressure required is 2.5 bar. Now we are moving towards the question number 2. A vessel of 120 ml capacity contains a certain amount of gas at 35 degrees Celsius and 1.2 bar pressure. The gas is transferred to another vessel of volume 180 ml at 35 degrees Celsius. What would be its pressure? Again we have to calculate the P2. Same thing, P1 is given, V1 is given, V2 is given. According to the Boyle's law, the same formula P1 V1 is equal to P2 V2. So P2 will be P1 V1 upon V2. Therefore 1.2 into 120 upon 180, that is equal to 0.8 bar. So therefore the pressure would be 0.8 bar. Question number 3. Using the equation of states PV is equal to nRT, show that a given temperature density of a gas is proportional to gas pressure. So you know very well, PV is equal to nRT, ideal gas equation. What is P, what is B, what is N, what is R, what is T? All the things we know very well. So N by V is equal to P by RT. Can we write this thing? Yeah. So now we have to just replace the N into M by capital M, right? So M by capital M into V is equal to P by RT, where small m is equal to mass of the gas and capital M is equal to molar mass of the gas. So M by V is equal to density, right? So from the equation second, this equation, M by MV is equal to P by RT. What we can write? D by M is equal to P by RT. Therefore, D is equal to M by RT into P. Molar mass M of a gas is always constant, and therefore at the constant temperature, T into M means T constant temperature T, M by RT is equal to constant. D is equal to constant for P. D is directly proportional to pressure. Density is directly proportional to pressure. Hence, at a given temperature, the density D of gas is proportional to its pressure. So now let's come on the question number 4. At 0 degrees Celsius, the density of a certain oxide of a gas at 2 bar is at the same, or you can say at that of dinitrogen at 5 bar. What is the molecular mass of the oxide? Same question is given in our NCERT in-text question also. So here the density of the substance at temperature T will be expressed as D is equal to MP by RT. So you can see density of the oxide D1 is given. D1 is equal to M1 P1 by RT, where M1 and P1 are the mass and pressure of the oxides respectively. Density of the nitrogen gas D2 is equal to M2 P2 by RT, where M2 and P2 are the mass and pressure of the oxide respectively. According to the given question, D1 is equal to D2. So M1 P1 is equal to M2 P2. P1 is equal to 2 bar, P2 is equal to 5 bar. Molecular mass of the nitrogen M2 is equal to 28 gram per mole. So M1 will be M2 P2 by P1, 28 into 5 by 2, that is equal to 70 gram per mole. Hence the molecular mass of the oxide is 70 gram per mole. Now we are moving towards the question number 5. Our question number 5 is pressure of a 1 gram of an ideal gas A at 27 degrees Celsius is found to be 2 bar when 2 gram of another ideal gas B is introduced in the same flask at the same temperature. The pressure becomes 3 bar. Find a relationship between their molecular masses. For the ideal gas equation, you know very well, PV is equal to nRT. For A molecule, it will be PAV is equal to NART, where PA and NA represent the pressure and the number of moles of a gas A. For the ideal gas B, the ideal equation will be PBV is equal to NBRT, where PB and NB represent the pressure and number of moles of the gas B. So from the equation, PAV is equal to MA by MA RT, that is PA by MA is equal to RT by V. From the equation second, we have just taken PBV is equal to MB by capital MB RT, and you can see here PB is equal to PB MB by MB is equal to RT by V, where MA and MB are the molecular masses of the gases A and B respectively. From the equations third and fourth, we have PA by MA is equal to PB MB by MB. So MA is equal to 1 gram, PA is equal to 2 bar, MB is equal to 2 gram, PB is equal to 3 minus 2, that is equal to 1 bar, since total pressure is 3 bar. Now we are substituting the value in the equation 5 by PA by MA is equal to PB MB by MB. So 2 into MA by 1 is equal to 1 into MB by 2. So 4 MA is equal to MB. 4 MA is equal to MB. So if anybody had asked you about this question, what are the relationship between the molecular masses of A and B, so you can say them that 4 MA is equal to MB. Now we are moving towards the question number 6. The drain cleaner, Drain-X, contain small bits of aluminium which react with caustic soda to produce dihydrogen. What volume of dihydrogen at 20 degrees Celsius and 1 bar will be released when 0.15 gram of aluminium reacts? The reaction of the aluminium with caustic soda can be represented as 2 aluminium plus 2 sodium hydroxide plus 2 water is equal to 2 sodium aluminate plus 3 H2. That is 3 into, if you just represent aluminium atomic mass, you know very well, 27, and here 22,400 ml, that is 22.4 liter at STP 273.15 Kelvin and 1 atmospheric bar pressure. So 54 gram. Why 54 gram? Because there are 2 moles of aluminium. So 27 to ja 54 gram of aluminium gives 3 into 22,400 milliliter of hydrogen. Therefore 1 gram it will give 3 into 22,400 upon 273.15, and 0.15 gram will give 3 into 22,400 upon 54 into 0.15, right? So here you can see it will be 186.67 ml of H2. At STP, P1 is equal to 1 atmospheric bar pressure, V1 186.67 ml, T1 273.15 Kelvin. Let the volume of dihydrogen be V2 at pressure 2 0.987 atmospheric bar pressure, since 1 bar is equal to 0.987 atmospheric bar pressure, and T2 is equal to 20 degrees Celsius, that is equal to 273.15 plus 20 Kelvin, that is equal to 293.15 Kelvin. Now P1 V1 by T1 is equal to P2 V2 by T2. According to the combined gases law, V2 is equal to P1 V1 T2 upon P2 T1. Just by putting the value, we get the answer 203 ml. Therefore 203 ml of dihydrogen will be released. Now we are moving towards the question number 7. So you can see this question number 7. What will be the pressure exerted by a mixture of 3.2 gram of methane and 4.4 gram of carbon dioxide contained in a 9 decimeter cube flask at 27 degrees Celsius? You know very well, PV is equal to nRT. So P is equal to nRT by V, and instead of N we can write small m by capital M. So for methane, you have to just put the value 3.2 upon 16 into 8.314 into 300 upon 9 into 10 to the power minus 3, since 9 decimeter cube is equal to 9 into 10 to the power minus 3 meter cube, and 27 degrees Celsius is equal to 273 plus 27, that is equal to 300 Kelvin, that is equal to 5.543 into 10 to the power 4 Pascal. For carbon dioxide, PCO2 is equal to 4.4 upon 44 into 8.314 into 300 upon 9 into 10 to the power minus 3, that is equal to 2.771 into 10 to the power 4 Pascal. Total pressure exerted by the mixture can be obtained as P is equal to partial pressure of methane plus partial pressure of carbon dioxide, that is equal to 5.543 into 10 to the power 4 plus 2.771 into 10 to the power 4 Pascal, that is equal to 8.314 into 10 to the power 4 Pascal. Hence, the total pressure exerted by the mixture is 8.314 into 10 to the power 4 Pascal. Now we are moving towards the question number 8. What will be the pressure of the gaseous mixture when 0.5 liter of hydrogen at 0.8 bar and 2 liter of dioxygen at 0.7 bar are introduced in a 1 liter vessel at 27 degrees Celsius? The partial pressure of hydrogen in the vessel will be pH2. Now P1 is equal to 0.8 bar, P2 is equal to pH2, V1 is equal to 0.5 liter, V2 is equal to 1 liter. Right? Now P1 V1 is equal to P2 V2. So therefore P2 is equal to P1 V1 upon V2. We have to just put the value of pH2 is equal to 0.8 and into 0.5 upon 1, that is equal to 0.5 bar pressure. So now let the partial pressure of oxygen in the vessel be PO2. So now you can see P1 is equal to 0.7 bar, P2 is equal to PO2, V1 is equal to 2.0 liter, V2 is equal to 1 liter. So P1 V1 is equal to P2 V2, P2 is equal to P1 V1 upon V2. So PO2 is equal to 0.7 into 20 upon 1, that is equal to 0.4 bar pressure. Total pressure of the gas mixture in the vessel can be obtained as P total is equal to pH2 plus PO2, that is 0.4 plus 1.4, that is equal to 1.8 bar pressure. Hence the total pressure of the gaseous mixture in the vessel is 1.8 bar. Now we are moving towards the question number 9. The density of a gas is found be 9.46 gram per decimeter cube at 27 degrees Celsius at 2 bar pressure. What will be its density at STP? So the things which are given, D1 is equal to 5.46 gram per decimeter cube, P1 is equal to 2 bar, T1 is equal to 27 degrees Celsius, that is 300 Kelvin, P2 is equal to 1 bar, T2 is equal to 273 Kelvin, D2 is equal to what? We have to just find D2. The density D2 of the gas at STP can be calculated by the equation D is equal to MP by RT. So D1 by D2 is equal to MP1 by RT1 upon MP2 by RT2. So D1 by D2 is equal to P1 T2 upon P2 T1. So D2 is equal to P2 T1 D1 upon P1 T2. So 1 into 300 into 5.46 upon 2 into 273, that is equal to 3 gram per decimeter cube. Hence the density of the gas at STP will be 3 gram per decimeter cube. Now we are moving towards the question number 10. 34.05 ml of phosphorus vapor weights is 0.0625 gram at 546 degrees Celsius and 0.1 bar pressure. What is the molar mass of the phosphorus? What we have to calculate? Molar mass. P1 is equal to 0.1 bar, V1 is equal to 34.05 ml, 34.05 into 10 to the power minus 3 liter, 34.05 into 10 to the power minus 3 decimeter cube. R is equal to 0.083 bar decimeter cube per Kelvin per mole, and T is equal to 546 degrees Celsius, that is equal to 819 Kelvin. The number of moles can be calculated using the ideal gas equation. PV is equal to nRT. N is equal to PV by RT. So by putting the value 0.1 into 34.05 into 10 to the power minus 3 upon 0.083 into 819, that is equal to 5.01 into 10 to the power minus 5 mole. Therefore the molar mass of phosphorus is equal to 0.0625 upon 5.01 into 10 to the power minus 5, that is equal to 1247.5 gram per mole. Hence the molar mass of the phosphorus is 1247.5 gram per mole. Now we are moving towards the question number 11. A student forget to add the reaction mixture to the round bottom flask at 27 degrees Celsius, but instead he or she placed the flask on the flame. After a lapse of time, he realized his mistake, and using a pyrometer he found that the temperature of the flask was 477 degrees Celsius. What fraction of air would have been expelled out? The volume of the round bottom flask, let it be V. Then the volume of the air inside the flask is 27 degrees Celsius, is V. Now V1 is equal to V, T1 is equal to 27 degrees Celsius, that is equal to 300 Kelvin, at V2 is equal to what? T2 is equal to 477 degrees Celsius, that is 750 Kelvin. According to Charles' law, remember how to use whatever the things are given, just correlate with the formula, either in the Boyle's law or Charles' law, whatever the values are given, it suits, so then you have to use that formula. So V1 upon T1 is equal to V2 upon T2, so V2 is equal to V1 T2 upon T1. 750 V upon 300, that is equal to 2.5 V, right? So here that is 2.5 V. Therefore volume of air expelled out is 2.5 V minus V, that is equal to 1.5 V. So fraction of air expelled out 1.5V upon 2.5V, that is equal to 3 upon 5. Now we are moving towards the question number 12. Calculate the temperature of 4.0 mole of a gas occupying 5 decimeter Q at 3.32 bar. Answer: N is equal to 4.0 mole, V is equal to 5 decimeter Q, pressure is equal to 3.32 bar, R is equal to 0.083 bar per decimeter Q per Kelvin per mole. The temperature can be calculated using the ideal gas equation PV is equal to nRT, T is equal to PV by nR. So 3.32 into 5 upon 4 into 0.83, that is equal to 50 Kelvin. Hence, the required temperature is 50 Kelvin. Now we are moving towards the question number 13. Question number 13 is calculate the total number of electrons present in 1.4 gram of dinitrogen gas. Molar mass of dinitrogen is 28 gram per mole. Thus 1.4 gram of N2 is equal to 1.4 upon 28, that is equal to 0.05 mole. That is equal to 0.05 into 6.02 into 10 to the power 23 number of molecules, that is equal to 3.01 into 10 to the power 23 number of molecules. Now 1 molecule of N2 contains 14 electrons. Therefore 3.01 into 10 to the power 23 molecules of N2 contains 14 into 3.01 into 10 to the power 23, that is 4.214 into 10 to the power 23 electrons. Here it is 10 to the power 23, it's, by mistake it's written 1023. Okay. Now we are moving towards the question number 14. How much time would it take to distribute 1 Avogadro number of wheat grains in 10 to the power 10 grains are distributed each second? Avogadro number is 6.02 into 10 to the power 23. The time required 6.02 into 10 to the power 23 upon 10 to the power 10 seconds. 6.02 into 10 to the power 23 seconds. That is, if you convert 10 to the power 10 grains each second, means 60 into 60 into 24 into 365. In 1 year there are total 365 days, and in 1 day there are 24 hours, and 1 hour contains 60 minutes and 60 minutes contains 60 seconds. So that's why 6.02 into 10 to the power 23 upon 60 into 60 into 24 into 365 years, that is 1.909 into 10 to the power 6 years. Hence the time taken would be 1.909 into 10 to the power 6 years. Now we are moving towards question number 15. Calculate the total pressure in a mixture of 8 gram of dioxygen and 4 gram of dihydrogen confined in a vessel of 1 decimeter Q at 27 degrees Celsius. R is equal to 0.083 bar per decimeter Q per Kelvin per mole. So the mass of the oxygen is equal to 8 gram. Number of moles of oxygen 8 upon 32, that is 0.25 mole. Mass of dihydrogen 4 gram. Number of moles 4 upon 2, that is 2 mole. Therefore the total number of moles in the mixture 0.25 plus 2, that is equal to 2.25 mole. Given V1 is equal to 1 decimeter Q, N1 is equal to 2.25 mole, R1 is equal to, R means universal gas constant 0.083 bar decimeter Q per Kelvin per mole. Temperature 27 degrees Celsius, that is 300 Kelvin. Now total pressure can be calculated as PV is equal to nRT. So P is equal to nRT by V by putting the value 225 into 0.083 into 300 upon 1, that is 56.025 bar pressure. Hence the total pressure of the mixture is 56.025 bar. Now we are moving toward the question number 16. Payload is defined as the difference between the mass of displaced air and the mass of the balloon. Calculate the payload when a balloon of radius 10 to the power 10 meter, mass 100 kg is filled with the helium at 1.66 bar at 27 degrees Celsius. The density of the air 1.2 kilogram per meter cube, and the Rydberg constant is 0.083 bar decimeter cube per Kelvin per mole. So the radius of the balloon is given, that is 10 meter. So balloon is spherical, the volume of the balloon will be 4 by 3 pi r cube. 4 by 3, pi value is 22 by 7 and r value is 10, so 10 to the power 3. That will be 4190.5 meter cube approximately. Thus the volume of the displaced air is 4190.5 meter cube. Now the density of the air is given 1.2 kilogram per meter cube. Then mass of displaced air 4190.5 into 1.2 kilogram, that is 5028.6 kilogram. Now the mass of the helium inside the balloon is m is equal to mpv upon rt. M is 4 into 10 to the power minus 3 kilogram per mole. P is equal to 1.66 bar. V is equal to volume of the balloon, that is 4190.5 meter cube. R is equal to 0.083 bar per decimeter cube per Kelvin per mole. Temperature is equal to 27 degrees Celsius, that is 300 Kelvin. Now M is equal to 4 into 10 to the power minus 3 into 1.66 into 4190.5 10 into 10 to the power 3 upon 0.083 into 300, that is 1117.5 kilogram approx. Now the total mass of the balloon filled with the helium is 100 plus 1117.5 kilogram, that is 1217.5 kilogram. Hence payload is equal to 5028.6 minus 1217.5, that is equal to 3811.1 kilogram. Hence the payload of the balloon is 3811.1 kilogram. So these was our question number 16. Now we are moving towards the question number 17. Calculate the volume occupied by 8.8 gram of carbon dioxide at 31.1 degrees Celsius and at 1 bar pressure. We know the value of R is 0.083 bar liter per Kelvin per mole here. It is known as PV is equal to nRT. So PV is equal to m by mRT. V is equal to mRT by mP. M is equal to 8.8 gram. R is equal to 0.083 bar liter per Kelvin per mole. T is equal to 31.1 degrees Celsius, that is equal to 304.1 Kelvin. M is equal to 44 gram. P1 is equal to 1 bar pressure. Now by putting the value, V is equal to 8.8 into 0.083 into 304.1 upon 44 into 1, that is equal to 5.04806 liter, that is 5.05 liter. Hence the volume occupied is 5.05 liter. Now we are moving towards the question number 18. Question number 18 is 2.9 gram of gas at 95 degrees Celsius occupy the same volume as 0.184 gram of dihydrogen at 17 degrees Celsius. At the same pressure, what is the molar mass of the gas? The volume occupied by the dihydrogen is given by V is equal to m by m RT by P, 0.184 upon 2 into R into 290 upon P. Let m be the molar mass of the unknown gas. Volume V occupied by the unknown gas can be calculated as V is equal to m by m RT by P, 2.9 by m into R into 368 upon P. According to the question, 0.184 upon 2 into R into 290 by P, that is equal to 2.9 by m into R into 368 by P, that is equal to 0.184 into 290 by 2, that is equal to 2.9 into 368 by m. M is equal to 2.9 into 368 into 2 upon 0.184 into 290, that is equal to 40 gram per mole. Hence the molar mass of the gas is 40 gram per mole. Now we are moving towards the question number 19. A mixture of dihydrogen and dioxygen at 1 bar pressure contain 20% by weight of dihydrogen. Calculate the partial pressure of dihydrogen. Means we have to calculate the partial pressure, right? So let the weight of the dihydrogen be 20 gram and the weight of oxygen be 80 gram. So NH2 is equal to 20 by 2, that is 10 moles. Number of moles of hydrogen 10 moles and the number of moles of oxygen, that is 80 upon 32, 2.5 moles. Now the total pressure of the mixture P total is equal to 1 bar. Partial pressure of hydrogen pH2 is equal to NH2 by NH2 plus NO2 into P total. 10 upon 10 plus 2.5 into 1, that is equal to 0.8 bar. Hence the partial pressure of H2 is 0.8 bar. Now we are moving towards the question number 20. What would be the SI unit for the quantity PV2 T2 by N? SI unit for pressure is Newton per meter square. SI unit for volume is meter cube. SI unit for temperature is Kelvin. SI unit for number of moles N is mole. So therefore the SI unit for the quantity PV square T square by N is given by Newton per meter square, meter cube whole square, Kelvin whole square upon mole, that is Newton meter to the power 4 Kelvin to the power 2 per mole, right? This was our question number 20. Now we are moving to the question number 21. In the terms of Charles' law, explain why minus 273 degrees Celsius is the lowest possible temperature. Charles' law states that at constant pressure, the volume of a fixed mass of a gas is directly proportional to its absolute temperature. So here you can just see a graph, temperatures versus volume graph you can see. It was found that for all the gases at given pressure, the plots of volume versus temperature in degrees Celsius in a straight line, if this line is extended to the zero volume, then it intersects the temperature axis at minus 273 degrees Celsius. In other words, the volume of any gas at minus 273 degrees Celsius is zero. This is because all gases get liquefied before reaching a temperature of minus 273 degrees Celsius. Hence, it can be concluded that minus 273 degrees Celsius is the lowest possible temperature. Now we are moving towards the question number 22. Critical temperature for carbon dioxide and methane are 31.1 degrees Celsius and minus 81.9 degrees Celsius respectively. Which of these has stronger intermolecular forces and why? Higher is the critical temperature of a gas, easier is its liquefaction. This means that intermolecular forces of attraction between the molecules of a gas are directly proportional to its critical temperature. Hence, intermolecular forces of attraction are stronger in the case of CO2. So this was our question number 22. Now we are moving towards the question number 23. Explain the physical significance of van der Waals parameter. Physical significance of A. A is the measure of magnitude of intermolecular attractive forces within a gas. Physical significance of B. B is the measure of the volume of a gas, of a molecule. B is the measure of the volume of a gas molecule. So this was our chapter number 5, whole exercise solution. Hope all of you have written all the answers in your notebook. If you have any doubt, then drop your doubt into the comment box section. That's all for today. Thank you very much. Have a great day. If you have not liked and subscribed my channel, don't forget to like and subscribe. Thank you very much.